Hi, this is Mrs. LaBarbara. This is Physics Chapter 5, Uniform Circular Motion and Universal Gravitation, Video 6. Today's topic is satellite motion. The objectives are to know the principle and the equations of satellite circular motion. To understand, the speed and acceleration of satellite depends only on the mass of the planet and the distance the satellite from the planet, not on the mass of the satellite. And be able to derive speed and acceleration of a satellite, explain the weightlessness in orbit, calculate force acceleration of motion in an elevator. Let's talk about circular motion principle and equations for satellites. So a satellite is any object that is orbiting the Earth, Sun, or other massive body. Every satellite's motion is governed by the same physics principles and described by the same mathematical equations. The net centripetal force is provided by gravitational force acting upon this orbiting satellite. That is the underlying physical principle for all satellites. So for all satellite motion, it's a circular motion. So that means its velocity is tangent to the circle and acceleration is directed toward the center of the circle. Centripetal force is provided in this case for all satellites is gravity. So that means centripetal force equals gravity. That's the physics principle for satellite motion. Here's centripetal force equation, here's gravity equation. We set the two equals to each other. Simplify m satellite cancels, so we can get velocity and acceleration. This is how you derive it. Now let's take a look at the speed and acceleration of a satellite. As you can see from this equation, both the speed and acceleration of the satellite depends only on the mass of the central body, about which the satellite orbits, and the distance between the satellite and center of the central body. It has nothing to do with the mass of a satellite. So that means if a baseball and a big spaceship were sent to the same distance r from the center of the Earth, both will orbit Earth with the same speed and have the same acceleration, because that speed and acceleration has nothing to do with their mass. Here is check your understanding. A satellite is orbiting a planet. Which of the following variable will affect the speed of satellite? So as I just said, the speed of satellite only depends on two things, the mass of the planet and how far away from the planet is. So the answer is B and C. It does not depend on the mass of satellite at all. Next topic is weightlessness in orbit. So astronauts who are orbiting the Earth often experience sensations of weightlessness. These sensations experienced by orbiting astronauts are the same sensations experienced by anyone who has been temporarily suspended above the seat on an amusement park ride. You probably have this experience if you think back. And that's the thrill when you feel weightless, right? You can only feel the force of gravity pulling upon your body through contact force. Contact means touching. That means you have to touch something to feel it, such as standing on the floor. That's how you can feel your weight. Sitting on the chair, you can feel your weight. Lying on the bed. So without contact force, there is no means for you to feel the forces. So you are not feeling the forces when you're falling on an amusement park. Oh, if you were an astronaut falling around the Earth, that's because you don't have contact force. You are not in touch with anything. But there is still gravity acting on you all the time. Gravity is the force making the astronauts falling around Earth. And gravity is making you falling too in the amusement park. Test your preconceived notions about weightlessness. Astronauts on the orbiting space station are weightless because there is no gravity in space and they do not weigh anything. Space is vacuum. There is no gravity in vacuum. The astronauts are far from Earth's surface at a location where gravitation has minimal effect, or there is no normal force acting on the astronauts, so they do not feel their weight. Exactly, D is the one they do not feel their weight. That's how they have sensations of weightless. That's because they are not in contact with anything. They are just floating with the spaceship. So the answer is D. And we know gravity exists even when it's far away. Let's take a look at scales. So if you want to know your weight, you may stand on the scale to find out because the scale measures the normal force. And in most cases, when you are at rest or moving at constant speed, both force cancels out because you are not accelerating. However, that scale does not always measure your weight. When you're standing on a scale in an elevator going up or down, when you're standing on a scale on inclined plane, the scale reading is different than when you are at rest or when you're traveling at constant speed. So technically speaking, the scale does not really measure your weight. What does it measure? It measures the normal force. Since it measures the upward force you apply to your body, so as you move up and down, accelerating up and down, the scale reading is different from your weight. And so is when you're standing on a scale on the inclined plane like this, the scale weighting is less than your weight. Now, what does the scale measure? The scale measures the normal force. The normal force is the scale pushing you up. That's the force the scale exerts on you. That's a normal force. So in all these different situations, while you are in the elevator, first you are on the elevator, you are moving at a constant speed. How do I know? Because acceleration equals 0. We can figure out the mass by using mass equals gravity divided by g. Use g equals 9.8. So the mass is 80 kilograms. As a matter of fact, it's the same person, so the mass is the same for all situations. So what is the normal force in this case? Since there is no acceleration, there is no net force. So normal force must equals to gravity. The two must cancel out to have to be in equilibrium. Equilibrium means acceleration equals 0. What happens if you accelerate upward? So when you accelerate upward, net force has to be upward. So net force equals to normal force minus gravity. I just choose the upward as positive. I choose whatever acceleration, the direction of acceleration as positive. If acceleration is up, I choose up to be positive. If acceleration is down, I choose down to be positive. You can just have up as positive, you will have the same results. So net force, I choose up as positive. Net force equals Fn is positive plus negative, which is Fn minus Fg. So Fnet equals Ma. So Ma plus Fg equals Fn. Ma is 4 times 80, which gives you 320, plus Fg is 784. That equals Fn. So Fn equals to 1,104 newtons in this case. Take a look. Another case, if you accelerate downward, again, as I said, I choose, in this case, acceleration is down, so I choose down as my positive. So my net force equals gravity minus normal force, because now normal force is negative. So Fn in this case would be equals Fg minus Fnet. Again, Fg is 784 and Fnet is 320. So after I subtract it, I get 464 newtons. That's a normal force. So as you can see, sometimes I use F normal, sometimes I use Fn. That means the same thing. One thing I don't want you to mix up is Fn and Fnet. Those are different forces. Fn is normal force, Fnet is the net force. Now, what happens if you are free falling? Acceleration is 9.8 meters per second squared downward. What is the normal force in this case? Again, downward as positive, Fnet equals Fg minus Fn. So again, rearrange the equation, Fn equals Fg minus Fnet. So Fn equals to Fg is 784 newtons, Fnet is also 784 because Fnet equals m times A. So normal force equals 0. Because you are both falling the same time, you are falling with the scale. So this is when you feel weightless, even though there is gravity acting on you all the time. Let's take a look, couple more examples. A person is standing on a bathroom scale in an elevator car. If the scale reads a value greater than the weight of the person at rest, the elevator car could be moving. Since the scale reads greater than the weight, so you'll have upward force is more than downward force. Since upward is more than downward force, there is a net upward force. So that means that the elevator must be accelerating upward. So the upward speed must be increasing. So the elevator is moving upward at increasing speed. That's the answer. Another example, 750 Newton person standing on an elevator that is accelerating downward. The upward force on the person must be, since the elevator is accelerating downward, so the net force must be downward. So the net force equals to gravity minus normal force is positive. So that means normal force has to be less than gravity. So the answer is B. That's it for today. Thanks for watching. See you next time.